Hi, I'm Fernando Pereira, and today I will explain how to generate constraints to solve control flow analysis. Basically, we will extract two kinds of constraints from programs. The constraints have one of these two formats here. They can be simple inclusion or conditional inclusion, like the second kind of constraint. Let's see how we can extract these constraints now. Basically, we will have a function, I will call it x for the lack of a better name, which is like a visitor from the visitor design pattern. It traverses the abstract syntax tree of objects, extracting constraints from each label. For instance, if we visit a constant, then we have no constraint. So the constraint set produced for a constant is empty. What if we visit a variable? In this case, we have one constraint that says that R of x must be inside C of L. If we have a lambda expression, also we have one constraint that says that the expression must be inside its label. Recursively, we keep visiting the body of the expression with a new invocation of the visitor. And that might produce new constraints. And now we must analyze applications. That's always the trick part of everything. Anyways, if we have applications, then we produce constraints recursively for each one of its parts. That means invoking x over t1 and t2, like in here. And then we generate a bunch of conditional constraints, one for each possible function that appears in the program. Basically, we are saying that for each function in the program, if that function is in L1, then L2 must be in the environment of this parameter. Let's generate constraints for conditional expressions now. But if at this point you want to stop the video and think about the constraints that we generate for applications, just feel free to do it. Anyways, constraints for conditionals are not very hard, given what we have already seen. Basically, we shall generate constraints recursively for every term in the conditional expression. That means calling x 3 times recursively. And we, conservatively, generate constraints implying that the result of t1 or the result of t2 can be both at L. So we have this subset constraints here. Anyways, let's now talk about let expressions. Would you like to think about which constraints we would produce for let expressions? Would you like to stop the video, pick up a piece of paper, and try to write the constraints? That's actually not very complicated compared to applications. Basically, we analyze recursively T2 at L2 and T1 at L1. In addition to this, we need to specify a constraint saying that anything in L1 might be in R of x, and anything in C of L2 might be in C of L. And finally, we have binary expressions. How would be the constraints for binary expressions? Here they are. The constraints for binary expressions. That's relatively easy. Recursively, we generate constraints for each subterm in the expression. Anyways, now let's see how we generate constraints for this example program here on the bottom. Here are the constraints that we produce for this program. Notice that that function that we showed before, called x, traverses the abstract syntax tree of the program, and for each node it produces some constraints, which I'm showing the figure. Here's the constraints in set notation. We have 8 constraints in total, 4 conditional and 4 unconditional. By the way, can you imagine how many constraints could be produced per program? If we just look into the constraints, then conditional constraints give us n to the 4th constraint, where n is the size of the program. That kind of constraint has 4 parts that can be replaced with variables. 1, 2, 3, and 4. Then we would have n times n 4 times, but that would never really happen. The worst case is much lower, actually. The only construct that generates more constraints are applications, if you remember. But applications generate a linear number of constraints, So if we have any applications in the program, then we could have any squared constraints. That would be the worst case. Before we move on, I would like just to make a parallel with the constraints that we had seen for data flow analysis in the previous classes. All this analysis, be it data flow, be it constraint-based, control flow, are actually based on constraints. In a way, we are generating constraints for the program and then solving those constraints. If we generate constraints, we can imagine that we can simply forget the program and focus on the constraints. So that simplifies a bit the process of solving static analysis. The difference is that in this new case, here, when you talk about control flow analysis, we have conditional constraints. In the case of data flow analysis, we don't really have conditional constraints. Also, here in control flow, we have inclusion-based equations, and in data flow, we had equality-based equations. So these are the differences. And that concludes constraint generation. Next time, we shall talk about how we can solve the constraint system using some super nice graph algorithm.